Create two, and I guess we'll get started. So our first talk is Tomas Holderness, our field guide to building serverless geospatial apps on AWS. And so Tomas is a CTO at Addresscloud, building scalable geospatial systems and to map global property risk. So over to you.
Thanks. Come on in, take a seat. Let everyone get sat down, and I'll make a start. So, who am I and why am I talking about this super niche subject at FOSS4G in 20 minutes? So, my name is Tomas Holderness. I'm the CTO at Addresscloud. I'm not very good at talking about myself, but we've seen some great keynotes in the last couple of days that have really kind of pushed me to think about talking about why Addresscloud is at FOSS4G, what we do, and who we are. Come on in, Ian. You're welcome. So I did a degree in geographic information science at Newcastle, which is pretty much all the things we've been talking about here at FOSS the last couple of days, from remote sensing to ground survey to GPS to coordinate systems. And it's this is a complete footnote to my presentation, but there aren't many undergraduate degrees that teach the things that we do anymore. They're all kind of moving to master's level. And I think that's a really interesting, change for us as a community. And if anyone wants to chat to me about that afterwards, I'm up for a discussion. So I'm CTO at Addresscloud. My background's in GIS. We build maps for insurers. I'm going to talk a little bit more about what we do. But here's a screenshot from our Christmas party where we went to the Cambridge Map Library, and we're looking at a map of insurance, or insurance map from the GODE publications that allows an insurer to see where fire risk might spread around different dock warehouses. I'm a long-time FOSS4G attendee. We use a lot of open source technology, and the way that we kind of give back to FOSS4G at Addresscloud is by sponsoring these events, is by showing up to these events, and by having discussions with the community. So what do we do at Addresscloud? Well, we kind of answer 4 questions for insurers. Problems that we solve are helping insurers understand geographic risk. So where is the property? So given an address, we'll say this property is in this part of the world. Here it is. Here's a pin on the map. And then we can say, what kind of property is it? Is it a house? Is it a flat? Is it a school? Is it semi-detached? What are its characteristics? What are its geographic perils? Is that property likely to be exposed to flood, to fire, to subsidence? Even down to things like, is that a flat above a chip shop? So that would carry a higher fire risk. And then lastly, as an insurer, I'm also interested in what other properties I might insure nearby, because that might create what we call a hotspot of accumulation risk. If I've got lots and lots of properties in a concentrated area and there's a big flood, that could be a really big problem for me. So here's an example of one of our applications showing some wildfire data from our colleagues at Precisely in the US. And what we've done here is ingested their data set behind the scenes, but we're also rendering it on a map, and we're enabling us to say that this property in California has got a wildfire risk of interface high, so moderately high risk. And so we've pre-processed that data, and this is kind of what leads to what Addresscloud does, and our kind of secret sauce, I guess, is we take every building in the world, take Overture building footprints, and we'll be trying to tag all of those buildings with characteristics and perils. So we've ingested this big raster and vector data sets from our partners, and we've tagged every building to say, yeah, this building has this risk. And we do that at scale. Here's some of the customers that we work with. Some of these are household names, others you probably won't have heard of. But the point is that we're doing well north of 100 million transactions a month. So we're doing geospatial lookups like that at scale. We're doing it multi-region. We're doing it around the world. And it needs to be in real time, because insurers have this really quite weird but interesting use case of needing to be able to provide insurance to people at all times of the day and night. If there's, traditionally, if there's an ad campaign running after Coronation Street to get your home insurance, people will log on at that 7:30 p.m. and go and get a home insurance quote. And if we don't tell an insurer where that property is, what risk it might have, what risks it might be exposed to, an insurer can't quote on that piece of property. So our system needs to not only be able to answer those questions at scale in real time, but it also needs to be highly resilient. So how do we do what we do? This is an infographic that we lovingly call in-house the reverse Pac-Man. So we ingest a whole bunch of different data sets, and some of those are commercial data sets that we act as a reseller or we purchase. Some of those are open source data sets. And we do a whole bunch of ETL to those data sets that allow us to represent for every property anywhere in the world all of the information that we're interested about. And that's going to be the kind of core of today's talk, is that data model. What data model do we use, and different data models that we use to have that representation of that spatial geography. So we've got all of these data sets coming in. We do our ETL. We push them up to the cloud. The clue's in the name. We use AWS. Other clouds are available. Push them up to the cloud so that insurers can consume them through an application like the one I showed before, or through an API integration, or through a data as a service solution. So that's what we do at Addresscloud. I want to take a little sort of side detour now to talk about why we're here and talk about how we do geospatial stuff, but in a serverless context within AWS. And the first place to start is with relational models. We talked yesterday, desperately trying to remember the name, but we talked yesterday about the Java topology suite and GDAL and OGR, and all of that relies on the work that Eggenhofer and others have done over the years to say, when we have spatial relationships, we can define them using set theory effectively. So we can say, are 2 points intersecting each other? Is the World War II, did the World War II bomb land on my house, for example, from Barry's talk yesterday? Does the rail intersect the road? Is there a railway crossing there? Is this property within a particular land parcel? So this is really the foundation of everything that we do. The Java topology suite is one representation, implementation of that. And we see that in PostGIS. That's a very common place that we see that in our industry and in the FOSS community. And we see it, like as I've already mentioned, in GDAL and OGR. Now, we can say, I've got spatial data. I know it's got spatial relationships. As geographers, that's what we're interested in. How are things related to each other, and answering interesting questions using those relationships. We've got the Java topology suite. We've got PostGIS that allows me to represent those relationships ultimately using a relational model. So we can normalize our data and put it in a database. And that's a really, really clever idea. I think that PostGIS and other spatial databases it's a very neat idea, and that's why it's worked well for many years. The problem with that model is that we're ultimately coupling data storage and compute together. So when we want to ask more questions of our data, to do more complex queries, to do more spatial intersections or joins or buffers or whatever it may be, we're asking that database to work harder. So we have what we might call a traditional application stack that might look like this, and I've run stacks at scale in AWS where we've got some servers, so that could be in Node.js, that could be in Python, take your pick. We've got some relational databases. For example, we could run PostGIS using AWS RDS, but we know that ultimately the database becomes a bottleneck here, and the compute, because we've got to manage the scale up, the scale down. Catherine's keynote yesterday said a really interesting point was that we're kind of now limited by compute power and not data. I'm sure I saw her in the audience somewhere looking for it. And we've got services for data analysis like Google Earth Engine coming online that allow you to do that data analysis in a kind of scalable way. What I'm talking about here is we've moved beyond the analysis. I want to ship that data to my customers now. I want to build an application. At Addresscloud, we do it for insurers. There are many of you in the room that might do it for different use cases. There's someone next door talking now about their use case of doing it with a gluten-free map. But here, we've coupled our spatial data with our compute resource. We've got to manage that. It's not very scalable. We know that there are emerging technologies that have been around for a number of years now, such as microservices for different clouds, microservices for AWS. Jeremy Daly has written a blog for a number of years now. He's excellent, lots of different patterns, and that we've been really inspired by, that I've been really inspired by, about how to think about using off-the-shelf serverless technologies with my open source tech, with my data, to build scalable systems, to decouple that compute and storage. So to think about that as geographers, we've got this geospatial data. We do great processing. We can use GDAL. We can use our tools in the background. We can use our Python extensions. We can use QGIS. But when we want to push it into the cloud to get it to our customers at scale in a reliable, high-speed manner, we have to think about changing the way that we store it. We can't always just use PostGIS off the shelf if we want to do this at scale. We can. It's totally possible. You have to spend a lot of money doing it. You have to have a lot of servers. So we can think about modeling our spatial data in a different way. We can think about using cloud-native data formats like COGS, Cloud Optimized GeoTIFFs. Hopefully some of you in the room have heard of those. I'm going to mention them again in a minute. We can think about pre-gridding our data. There are interesting grids. We're going to talk about those in more detail. And we can also use our standard PostGIS database and run that in a kind of semi-serverless manner. So an example of some of these patterns, and I'm going to take you through 3 of my favorites. The first one is tiles. Mark, our CEO at Addresscloud, I think first talked about this in detail. He did a workshop at Phosphor G in Tanzania and made the point that we can serve tiles, the tile sets that you saw on the map that showed wildfire, for example. We can serve tiles from AWS using a CDN, and it doesn't cost us anything. It costs us something ridiculous, like 60 cents a year for a couple of thousand users. So it's about thinking on that triangle of cheap, fast, good. Well, actually, I can possibly get all 3 for some use cases with the cloud. We've already got really excellent ways of chopping up the earth to do tiles. Everyone is lots of people are familiar with slippy tile format. So I've got a ZXY that represents, here I am on the earth. I'm interested in grabbing this particular tile or collection of tiles and rendering it on my client. So that lends itself really nicely to a pattern in AWS where I put my tiles in a bucket. I put an API gateway instance in front of that bucket, and my client can make requests against that API. And here, so I've used Tippecanoe, I've used whatever tools to create my tile set ahead of time. They could be raster tiles, they could be vector tiles. I've defined my styles. I've popped them in a bucket. I put an API in front. There's no compute here. There's no Lambda function in this pattern, so I'm not paying for any compute. I'm literally paying for the storage of those tiles and my API gateway instance, which doesn't cost me anything to run. It's per request. So it's an incredibly efficient pricing model that allows you to scale out your tiling. We can do something really similar with cogs. Cloud optimized GeoTIFF is one of my favorite geospatial data formats. I am a massive geek. I got in the lift this morning and made a spatial optimization joke. A few people in the lift kind of went like, oh, who's this guy? Oh, let's get out the lift quickly. I hope the door's open soon. So, that's why I'm here at Fossil G. But it is, and because I started my life doing in geo and remote sensing, big binary files from NASA, trying to do stuff with compressed 10-bit compressed bytes and all sorts. It's horrible. We've got this great standard now that allows me to say, I've got a GeoTIFF, it's backwards compatible. I can look at it in QGIS, but I can also pop it in the cloud. And what's really clever is it's internally indexed. Again, coming back to indexing, coming back to data models, coming back to our relational model about how we optimize our spatial data. It's internally indexed to say, if I want these pixels in this area, it knows where to look in the file. And it's actually HTTP aware, so I can make requests across the internet. And lots of people have spoken about this. This is not me saying this is new. This is me, and we'll get to the point of all the things I'm talking about. This is me kind of documenting and talking about as a community. We've got our great open source spec. We've got our data. We can use the cloud to do this fast, cheap, good. We might have a data set that looks like this. It could be a flood model. It could be a DTM. It could be a subsidence map, whatever it may be. It's very, very big. It's very, very complex. If I want to query just one part of that, let's say a building footprint, and say what is the likelihood of flood in this building, I probably only want 10 pixels for the average terraced house in the north of England. I can represent that by saying this is a cog, and then I can query that cog using great open source software, the project Rasterio, and I can say this is my bounding box that I'm interested in, or this is the geographic footprint that I'm interested in, and we can make HTTP requests against our bucket and only get back those 5 to 10 pixels that I'm interested in. An incredibly scalable way of having a raster data that I've got from a data provider that's incredibly complex, but popping it in to a serverless model. It doesn't cost me anything, costs me barely anything to store it, costs me barely anything to look up those pixels. I'm utilizing open source software along the way. I'm just popping it into a cloud pattern. Grids, how many in for time? Yeah, great. Take a sip of water as well. Did put the air conditioning on. It was quite warm in here when I walked in. So this is grids, again, a piece of technology that we use at Addresscloud a lot. Lots of different grids available. Grids are just a way of chopping up the earth into different shapes. We looked at the kind of Web Mercator grid before for chopping up tiles, right? We know that the Uber H3 is one I'm going to talk about in more detail, but the point is that there are lots of different ways of partitioning the earth into equal areas that are probably better than just plain old latitude and longitude. We can use triangles, we can use these funny diamonds, we can use hexagons, we can use different shape hexagons, different size hexagons at different scales. And there's a lot of research in this and a lot of people who are starting to realize the value of these grids. One of the grids available, it's not the only one, choose your weapon, I'm happy to talk about this after as well, is the H3 grid that was from Uber that's got some very, very interesting properties in that hexagons are approximately proportionate, the same area across the Earth. There's a parent-child relationship, so as you zoom in, you get more hexagons. As you zoom out, you get fewer hexagons. Each hexagon has an internal grid referencing system, so it knows about all of the other the hexagons that are adjacent to it. Uber ultimately used this to work out where or how far away your car is. They know which hexagon that the car is driving to pick you up from your collection point. We use it because it gives us a consistent and immutable identifier, so we can take an address, like the address for this building that we're in now, and we can get a cell index for that address. And it might not be a perfect fit. This is kind of lossy, right? It's the hexagon doesn't perfectly fit around this building that we're in, but it gives me a point reference on the Earth's surface, and I get that unique ID, and then I might have data that I've also got in using the same grid referencing system. This is just another way of referencing geographic data. So maybe I've got some attributes about this building that tell me that this building is commercial and it's used for conferences, and I've tagged that against the same cell ID that's within the centroid of this building. What I can do there is I can think, well, I've got a key value lookup now. I haven't done anything super smart here, but I've pre-processed my data using an open source grid algorithm ultimately. And what's nice about this pattern, we don't actually do this, but it's kind of quite an interesting one, is we can push the computation, the geography conversion from XY coordinate to H3 identifier to the client. So you can say, hey, client, like you're over there, you've got some compute on your phone or on your desktop or whatever it is. Convert those coordinates to my cell index. And then I can do a really simple key value lookup against my key value database. Again, I don't have any compute running here. So when this thing isn't running, it's not costing me anything except for the data storage. And then I'm paying per request. This will scale infinitely. You can run this multi-region, you can do replication, you could run this all around the world, you can put a CDN in front of it. This thing, we do it, that's kind of how we power a lot of our data lookups, will scale and scale and scale and scale. It's fantastic. And it will scale down again when you're not using it. Cheap, fast, good. Love it. The future, I think within time limit, a couple of interesting things going on. There's some technology called data lake, which we haven't talked about so far today. I've been very focused on building an application and serving data to users. Data lake technology allows us to store data in columns instead of rows, and allows us to query and do analysis across data at scale. The two kind of predominant formats in that space, Iceberg and Parquet, have both now got, as of a couple of weeks ago, native support for geography. So I can put my geography into those data formats, and then I can do interesting data analysis things, which the data team at Addresscloud will be using and are interested in, and that's great. I'm really interested. I'm like, well, this is basically a cog for vector data. If I put it in a bucket, can I ask it at scale? Like how can I max that thing up? Can I ask it for lots of different bits around the world of flood model or whatever it is that I'm interested in? So that's incredibly interesting. DuckDB, another technology. There are a few in-memory DBs that have emerged off the back of the data lake world as well. Being able to run DuckDB is like in-memory one-time database. So put that in some compute, like a Lambda function that's going to spin up, open the database, do some cool spatial stuff, and then close down again. And then it's gone. That's super interesting to me because it means we can do lots and lots of little databases in parallel, as opposed to worrying about having one big database. Like ultimate test. I also do information security, but this is not my laptop. Man, I'm glad you're here. Right, 2 minutes, perfect. This is great. We've had laughs, we've had tears, we've had 2 minutes to go. Writing it all down. Okay, so I've been talking about this for a number of years at Phos4G things. Mark did a thing about tiles a while ago. As I'm not the only one. There's a great project called Tyler that's done lots of stuff around lambdas and scalable stuff from development seed, if my memory serves me right. Lots of people are kind of working on this. I had a great chat with someone yesterday who's doing satellite imagery analysis, but using step functions and lambdas. That was really interesting to hear, because it's like, okay, right, the people in the geo community are like coming to the cloud and saying, when I want to operationalize my processing, I need to think about this data model so that I can be smart in how I run that compute. And so this is a personal project, and it's an experiment, but it was kind of, there's a few seeds along the way. One of them was I presented some of the tile stuff a few years ago, and then Dennis came to me and asked a question afterwards, and he hadn't quite got it. And I was like, oh man, like I've just been at Phos4G and I poured my heart into this presentation. And Dennis was like, oh, yeah, that's great. And we had a great chat about it. And that's what FOSS is all about. We've seen collaboration. But I thought, okay, I'm going to have a crack, and this is an experiment. I'm going to see how many people turn up to my talk. It's quite a few over here, which is good. And I'm going to write this down. I'm going to start writing this down and see if anyone's interested in this. And if no one's interested in it, then we'll just use it as our internal documentation. But see that's like at least 4 people taking photos of it now. It's an interesting benchmark. I like to write Markdown, so I found this book from the Rust maintainers called this project called MD Book, which is like I write Markdown and then it makes it into a book. It's really, really easy and it's fast, and it's all kind of like GitLab does it for you, which is nice. So I wrote this down where I started to try and document these patterns. It's very light, it's very experimental. There's no code there. It's just a series of diagrams to say this is kind of how we do things. This is us giving back to the community. We've built a business that's incredibly successful. It's built on open source. But we run it in the cloud because we need to do it at scale around the world. And this is kind of how we do it. So we're sharing that the patterns are what I'm kind of contributing back today. I'm proud to be here. As I said, we've been built on open source. We're giving back. We're also hiring. We've got a brilliant team. If you're interested, no recruiters. If you're interested, email me and we can have a chat. And we'll leave it there. Thank you.
Okay, thank you very much. I think we've got some time for some questions. So if anyone's got a question, if you stick your hand up and we will try and answer a few. One at the back there.
Yeah, going back to, I also absolutely love cogs. Going back to the cog pipeline, I'm just curious, what's the Rasterio Lambda?
So the question was, in the cog pattern, what was the use case for the Rasterio Lambda? So for us, the use case is I've got a big cog. I want a handful of pixels. I'm actually not giving the raw pixels or the geometry to the user. I'm like maybe doing something like, how hot is that building, or what's the highest elevation point in that handful of pixels? So it's doing a little bit of aggregation. So it's looking up that geometry against those pixels and then returning that as a JSON. But similarly, it can also, the Tyler project does actually I want to render it as a tile. It's quite interesting. We do a bit of that as well. Yeah. How was the latency? Okay, let's chat, because when I did it, it was really slow. So I'm clearly, that sounds like a pattern. Let me know if you want to share. Any more?
You also diagram the H3 lookup, also to DynamoDB. You're saying that can scale infinitely, but with your Dynamo database, do you have
no, so you can, but DynamoDB also has a serverless mode where Amazon does all of that for you. So it's kind of auto magic where you're like, it's data and it's serverless and it just does it. There's no concept of units of compute or anything there. It just goes. Yeah, the SLA they give you is that you can look up any row in that database, however many rows it is, and it will be the same response. The response time will be, and you can do that as much as you want within the limits of your account. That's what we hit, not the limits of the technology, the limits that are set on the account to make sure that you don't abuse it. And then we go and say, can we have some more, please? And they say yes. But as a technology, they will scale that for you and partition it across multiple pieces of hardware. So you can just. Absolutely, yeah. So it's more akin to putting data in a bucket, in that we don't think about the hard drives, right? It's just in there, and that's DynamoDB is kind of analogous in that way.
Possibly a similar question. I've had clients with multiple offices around the world having the data synchronized across maybe 3 servers like that to get the data in the right place and make sure it's very, very simple. Could this potentially provide a solution in that respect?
So the question was, can this pattern or other patterns be used to do database syncing or data syncing right around the world? And I think you're talking about a write use case there where someone's making some edits and I need to, yeah?
Yeah, like a chief geologist might be in Australia, but the exploration journey might be.
Yeah, so that's a really good question. It depends on if you can get a data model that works where they make that edit and you write to Dynamo, yes, it will do multi-region. You can set multi-region instances and it will percolate that. But I think the challenge is what is the unit of data that person is they've edited a polygon, right? And so how are you in PostGIS? We think about I can store a pointer line or a polygon. What we've got to do here and say, well, I can't if I can store that type of data in Dynamo, but I can't spatially index it. So I need to kind of flip my data model on its head and think, how am I going to do the indexing so that the next person can go to the map and get that update that someone in Australia has made? So it's not a one-for-one, like, here's my ORM, I can just start to write to this different data store. I've got to think about the data model. And we still do have some PostGIS instances where we've got specific use cases because there is nothing better. But the point is that majority of our traffic isn't going down that route. But the edit use case in the shot, and then there's Aurora's Serverless v2, and we can chat a bit more about our experience here. Mike is in the audience. He's probably quite jaded by the experience of trying to get that thing to work, so we can also pull him into the conversation. Just one last.
Yeah. So these examples you've got, majority of read at the moment. So am I right in thinking that if you wanted to do edit as well, you wouldn't have as many edits. You might have a different set of APIs to do that, say it's a PostGIS database, but then percolate behind the scenes across all the dynamos. Does that sort of make sense?
Bang on.
Right, okay.
Yeah, I think that's, so that would like be an event-driven model.
Yeah.
Exactly that. Yeah, or doing something else with it. It doesn't have to be Dynamo, right? But it's thinking about that data model of what does AWS give me off the shelf that has that serverless layer.
And the right, if it's not going to be used as much, you don't need to have it for scalability side. Yeah.
Absolutely. And we have some stuff for customers that's custom, and it's like a smaller subset. And then at the application logic layer, it's like, oh, it's that customer. Do they have? Yeah.
Okay.
Leave there. Great. Thank you.
Thank you very much. So.